Okay, so there we go. Analyzing forces. Um, so we're gonna look at like three different kind of scenarios today, and actually let's talk about first type one. We'll go inclined planes. We did touch on this before, but I just want to visit it again really quickly to make sure that we're okay with it. So if we have an inclined plane and we put a block or a box on it like this, we should be able to figure out the forces at play on this object, and thereby sort out the acceleration of it. So let's do that as a bit of a warm-up, okay? Now I'm just going to give you the angle. Oh, for goodness sake. I'm just going to give you the angle. We'll call it 40 degrees. And for now, we'll say we'll say that friction equals 0, or mu equals 0. So there's no friction. And I might say find acceleration. Okay, so you could pause the video and give this a try. I'll just sort of like do a free body diagram first. So a free body diagram is going to analyze the forces at play on here. So we know first of all that we're going to have the force of gravity pulling straight down towards the ground on this thing. Okay, so we'll call that W. And W always equals m times g. So whatever mass we have here times g. Now we don't know the mass, and that's okay. We also know that there'll be a normal force on this object, and that normal force will be perpendicular to the surface. Okay, perpendicular to the surface. Now the thing about the normal force in this case is because there's an angle, the normal force is not equal and opposite to weight anymore. Okay, so we're going to just define that as Fn. In order to figure out what's going on with the normal force, we need to do a tip-to-tail vector scenario, right, like that. And then what we'll find is that the resultant force, when we sum these two, is going to point like that. Okay, so this is going to be the force acting on this object to accelerate it down the surface. Now we also learned way back when that the geometry of this scenario gives this angle right here a 40 degree. Okay, it's the same as this. Now that we know this, we can actually sort of define how we know what the normal force is and how we know what the accelerating force is. Now you don't for this problem need to deal at all with the normal force. It doesn't matter. However, when we add friction into a problem like this, we will. So right now, we're actually just interested in finding this, right? If we're in a frictionless scenario, we'll call that just FA. Okay, the accelerating force or the resultant when you sum weight plus normal. Okay, you get FA. So to find FA, you're going to take the hypotenuse of this, which is the weight, and you want to know the angle across, right? The opposite angle. So FA then should be equal to W, right, times the sine of 40 degrees, or the sine of theta, actually. Okay, let's do a general first, and then we'll like put our actual numbers in there. Okay, so FA equals weight sine theta, right? This will be theta. And then we also know that we define the weight as mg, so we could say mg sine theta. Okay, mg sine theta. And now we also understand that in this scenario, the only force acting on this object, right, is going to be this overall force. So the only, or I should say the net force. The net force on this object is acting this way, not the only force, the net force. Okay, and we also know that from Newton's second law, F net just equals m times a. Okay, so if FA is the same as F net, right, it's the only force acting, we could just replace it with MA. MA equals mg sine theta. And now we'll see that mass appears on both sides. Okay, so we can actually get rid of it. And now what we've developed is a formula for a frictionless inclined plane. So say something like a rolling ball, which has almost no friction on the surface. You can more or less apply this. Okay, so for a given value, you'll have the same acceleration. So in other words, in a frictionless scenario, and actually in a scenario where there's friction as well, the weight of the object does not matter. The mass of the object does not matter. All objects we place on here, regardless of mass, will accelerate at the same rate. We sort of proved it with this little formula. So in our scenario, the acceleration of this is g, so 9.8 meters per second squared, times the sine of 40 degrees. Okay, and that'll tell you the acceleration of any object, regardless of mass, to be placed on a 40-degree inclined plane. So we get 6.3 meters per second squared. Okay, there we go. Scenario 1. Now let's talk about friction. Okay, let's talk about friction. Friction. Okay, so what is friction? Well, friction is essentially resistance to motion. Okay, caused when two surfaces are sliding past one another. And actually, we'll break it into two types. Okay, we will talk about static friction. Okay, and this is the friction while an object is sitting still. As no objects have no relative motion. And we'll also mention kinetic friction. Okay, which is friction during sliding. Okay, so to first talk about why friction exists at all, let's think about some things here. So we've got a surface, all right, and we'll put a box on it with some weight. So let's talk about what is actually causing friction at the core of it all. All right, so if we were to be able to zoom right in on the two surfaces, so we were to just scan right in with some kind of powerful microscope, we would find that although appearing smooth from a macroscopic scale, at its microscopic scale, all surfaces are rough, okay? And so you can imagine that you have all these little pits and valleys interacting here. And not only that, there's electrical forces going on here. So first things first, do two surfaces ever really touch? And we sort of say, well, I guess it depends on your view of it. Depends how you define touching. But if you have positive protons and you have negative outer shells, then you can think of the fact that those negative outer shells repel each other from both surfaces. And the two surfaces, yes, they never, I guess, technically really touch, but then you could say, well, what does touching really mean? You could go on a long, tangent about that. But the point is that, these two surfaces, if I were to try to slide this one across that one, there's going to be an interaction here where essentially, as it moves along, it's going to have to lift and bump over all of these pits and valleys. And that causes resistance, okay? And, the harder that I'm pressing down on this surface, right, the more difficult it's going to be for me to push these across one another, right? So as I increase the weight of this object by making it more and more massive, right, it gets more and more difficult to push along because that friction rises up, okay? And you can probably start to think here, well, we're pushing along this way, but we also have that upward sort of normal force this way. So in a way, you could think about it like this. Friction is proportional to how much normal force we have. So the force of friction is always proportional to how much normal force we have, okay? The higher the mass, the more weight we have, and regardless of how smooth these are, the more friction we're going to have, okay? So this is a very important relationship to have, okay? You have more friction when you have more normal force, when you have more weight, okay? And the second thing is this. So if I'm pushing an object along, right, if I want it to slide across the surface constantly, I have to match the frictional force with an applied force. Okay, so I have to apply a force in this direction that equals friction if I want a constant velocity to push this object along. Okay, now I'm inputting force. A little bit later, we'll note that applying a force over a distance, it requires an input of what's called energy. Okay, and you might say, well, where's the energy going? Energy is conserved in nature. Well, it actually creates heat to do this, okay? Friction expels energy as heat from a system. So by pushing one object along the other, you're essentially agitating the molecules involved or the atoms involved, causing them to like vibrate faster, which manifests you and I as heat. All right. So friction actually creates heat and wastes energy. All right. So we'll cover energy a little bit more later. Now, what we're interested in is just simply like the creation of friction to begin with. So there's two things that friction depends on. One, it depends on the normal force, how much normal force there is. What's the other thing that it probably depends on? So let's think about this. Here's a surface. Let's say this surface is rubber. Will it be easy to push the block along a rubber surface compared to, say, an ice surface? The answer is no, right? The ice is going to be much lower friction than the rubber surface. So weight, more weight in either situation causes that particular situation to have more friction. But comparing across different situations, okay, the nature of the surfaces is important. Nature of the surfaces is important. So these are the two things that are going to affect how much friction we have, okay, in a given situation. And now the other thing that we said we were going to address was this kinetic versus static friction, okay? So here's the deal. Let's say we have an object sitting still on this surface, okay? It's sitting still. What you will find is that if you want to get it moving, you're going to have to apply a larger force to start it moving than you will in order to keep it moving, okay? So there's almost like a having to break it free type scenario going on here, all right? So we would say then that static friction, that's supposed to be an S. Let's just do it this way. Static is always greater than kinetic, okay? There's a few reasons for that. Okay, so one reason could be, and actually it's not completely understood physics-wise as to why this is so, but there's things that it could be. So one, obviously, I think, is inertia, right? You need to apply enough force both to break friction free and to accelerate this to whatever velocity you want. So more force will be required to get it going than to keep it going, just based on inertia. That's one thing. The second thing is it's possible that electrostatic forces build up and are not dispersed. Okay, when it's moving, possibly that heat disperses electrostatic attraction a little bit, or just the jostling of the two surfaces maybe does that, but I'm not 100% sure about that. Okay, when two objects are sitting still, though, one idea is that there becomes this built-up static charge that holds it in place. But exactly why static is greater is not completely 100% understood. So we'll just leave it at that. All right, so with the normal force, we basically said that the amount of friction you're going to have is going to be proportional to that. And then the nature of the surface is important. So what you end up having is you have this coefficient of friction, which is unique to each surface, right? Or each two objects that you're going to slide across one another, right? Coefficient of friction. And it has a symbol, and that symbol is mu, which is used for other things in physics, like it means micro as well, but it's the symbol for the coefficient of friction. So we could say this. We can say then the force of friction is equal to mu times the normal force. Okay, so let's do an example of this. E.g., a box is on a surface with mu equal to 0.7, say, okay, if the box is 40 kg, predict the force of friction. And you'll say, well, is that kinetic or static? Once we sort of define kinetic and static, we don't really talk about them separately anymore. So you could just kind of like gloss over that slightly, basically. And if you want, we could just say, to make it easier, that is kinetic friction, right? It's once it's going, okay? So let's draw a picture of this really quickly. Should be fairly simple. Box, surface, okay, and we're going to want mu is equal to 0.7. All right, and we've got someone pushing it. We want to know, like, well, what force are they going to have to apply to, say, keep it moving at a constant velocity? And basically, to keep it moving at a constant velocity, we have to have F net equal to 0. So in other words, the accelerating force plus the frictional force has to sum to 0. Make sense? So to solve for this, then, you're simply given the formula Ff equals Fn times mu, or mu Fn. So Fn in this case, since we're on just a vertical surface, is going to be equal and opposite to mg, right? So we've got our weight here, that's mg. And we've got our normal force here, which is equal and opposite to mg, right? There's no acceleration in the vertical plane, so it's got to be true. So it's just mg but up. So then we could say, if Fn is mg, we could say it's mg times mu. Or the more common way to write it is just mu times mg. So that's mu times the normal force. We'll write it as mu mg. So mu was 0.7 times 40 kgs times g. So you're going to get that the force of friction in this scenario is approximately 274 newtons. So here's a question. How would I know the mu value in a scenario, in a given scenario? How would I know it? Do you think there's like a table I could go to look these things up? You'd have exactly. You'd have to do it by testing. So in real life, you got to test two surfaces for the mu value, right? You can't just say like the mu value of rubber is like 1.2 or whatever it is, right? Because it also depends on what kind of like surface this has, right? This could be like ultra smooth, or it could be like a box wrapped in carpet, right? Which can be harder to push. So mu requires essentially knowing about both surfaces, and it will always be found by experiment, and in problems it'll just be given to you. Make sense? Okay, so let's up the ante here and do another one of these like inclined plane problems, but now let's put friction in here. Okay, so we'll do that. Okay, well, I'm gonna make friction sort of low so that I know this will actually slide. But here's another interesting question about the whole friction problem. What if the amount of friction found by mu mg is actually greater than the applied or accelerating force down the hill? What would happen to that object? What if friction ends up bigger than the applied force down here, the accelerating force? Yeah, it just won't move, right? Friction is a reactionary force. It cannot cause acceleration. So you're not going to have like this object suddenly like accelerating up the plane, right? That would be a scary physical world if that's what happened. Okay, so if I apply a mu value in this scenario, we'll call it mu is equal to 0. I don't know, let's say 2, 0.02, okay? We've got a 40-degree angle. Can I say find acceleration? So if I gave you a mass, you could apply a mass to this, but I'll show you that you actually don't even need a mass here either, okay? So let's start to analyze the forces. We know we've got this, right? We know we've got a normal force. I can kind of cheat, right, and move it. Let's have to draw it down here. Okay, and I didn't draw that very well. It's got to be parallel. And we know we have our accelerating force, or our applied force perpendicular to the surface. Okay, and we now also have that frictional force we've got to consider. So there it is. Okay, so let's just redefine what we had for friction. Well, Ff is equal to mu times the normal force. Okay, and if we've got a theta value here, okay, and we know that this is weight, W there. We know that weight equals mg. Then we know that the normal force here is going to have to be equal to weight times the cosine of theta. We also have to know that the accelerating force down the plane here, or the applied force if you want, is going to have to be weight times the sine of theta. Okay, so W sine theta is that. So how do we sort out the net force here? Let's just organize our thoughts. So the net force is going to be the sum of all the forces we have acting. So we know that we have an FA force acting down the plane. And we also know that we have a frictional force which is acting in the opposite direction. So the way I kind of like to think about this is, okay, so FA minus whatever I have for the frictional force should give me the overall net force acting on this object. Does that make sense? FA is the accelerating force. Subtract away whatever we get for friction should be the leftover or net force accelerating this thing down the plane. So look at my arrows, right? This represents my FA. I've taken it from here. This represents my frictional force. I've calculated it over here. All right? Okay, actually, sorry, this is probably causing some confusion to leave this as a negative. Let's just do this. Let's say, okay, so you can technically call it a sum, right? It's the sum of these two forces. Of course, realizing, right, that one is pointing the opposite direction of the other. So you're going to have to define one of these directions as negative. Essentially, as the physicist, you will define one of these directions as negative. Personally, in a scenario where FA is larger, all right, I generally like to put it as positive, this being negative. And, you know, since I know it's a negative FF value because of the direction of the vector, it's the equivalent of just saying subtract FF. So if you're like in tune with the problem, it shouldn't be an issue as to whether I'm putting positive or negative, because you can look at this and hopefully logically make sense of what's going to happen, right? The acceleration here is going to be less because now there's friction involved, right? If you end up with a value that's higher than what you got like last time you did it, or higher than what you would get, you know, if it say it comes, so sorry, so if you know, if you got an answer here that didn't make sense, like say you got an acceleration higher than 9.8 meters per second squared, well, that would be an issue. You can't accelerate faster down a plane than you would fall in free fall due to gravity. It doesn't make sense, right? The plane essentially will dilute gravity. And actually, just a little aside, a nice way to kind of think about this is more or less this, right? You know, whatever theta value you have, you know, as you increase it, this becomes closer and closer and closer to 90 degrees, right? We said before, acceleration is g sine theta, right? G times the sine of theta. Well, what's the sine of 90 degrees? It's 1, right? So you just have g. This goes straight up, you just have g. There is no, you know, slowing down from the plane. And what if it's 0? What if it's 0? What's the acceleration there? Well, it's still g sine theta, but now it's g sine 0 degrees. So it's 0. There's 0 acceleration. So in other words, you follow this sort of acceleration curve, and this is ignoring friction, of course, between 0 degrees and 90 degrees. All right, so it's essentially diluting gravity, and depending on the angle, you'll get your acceleration from that scenario. Okay, so that's a little aside. So whether I write this as plus and we realize that it's negative, or I put subtract and I don't put the negative in the force, you understand that we have two forces aiming opposite directions. Being logical humans, I'm hoping you can kind of sort out in your mind how that's going to have to work. Okay, so now let's like put some numbers in here and see if we can figure out an answer for this. So FA, we say, is W sine theta. So I'm going to write that here, W sine theta, plus, now it's aiming in the opposite direction, so I'm putting a negative here. W cos theta times mu, right? Because it's Fn times mu. That's the definition of Fn. Then FF is mu times Fn. Okay? And then let's replace the W with what we know it stands for. So mg sine theta plus negative, I'm just going to move the mu to the front, mu mg cos theta. Put brackets around that. And we know that this will give me my F net. Now, I haven't given you a mass. However, the net force is also the accelerating force. So the mass, the overall net force is equal to the mass times the acceleration, equals mg sine theta plus negative mu mg cos theta. And we can pull the m out of each of these, right? We can make this a scenario where we multiply both by m, or we can just divide m off the whole thing. and m will cancel out of here, and you get this. The acceleration of your block on a surface is g sine theta minus mu g cos theta. Now what can I do? Well, I can actually further work on this, and I could say that it's g sine theta minus mu cos theta. Okay, so now that we've sort of pulled this out of here, we should be able to go, the acceleration of that block is equal to 9.8 times the sine of 40 degrees minus mu times the cos of 40 degrees. And the mu value I think I gave you was 0.1, was it not? 0.2? Okay, so this works out to be about 0.4895, and you get an acceleration of about 4.8, which is kind of like reasonable. That's a fairly low friction, and we got an acceleration value that's lower than when we did it with no friction. So the pieces kind of fall into place there. All right. Okay, so let's try to solve something here really quickly. As a little practice problem, and I'll just see if I can add a little spin on this to make it slightly more challenging. So I'm going to put a block on a surface. Okay. I'm going to ask you this. If mu equals 0.2, like the last problem, what is the, let's see, what is the maximum angle we can have so that the block stays put? Okay, so in other words, how high can I lift this such that if I lift it any more, the block will start sliding? What's the highest amount that I could possibly lift this? Okay, so how are we going to do this? Well, we're going to start by like putting free body diagram arrows on here, right? That's how we're always going to start. So we got that one. I wanted that to look like an arrow. It's okay if it doesn't. We've got this one. So they don't want it to be yellow. Okay, we've got our normal force. Oh, for goodness sake. It's like the default color is always black, so you can't see my lines. Okay, so we have that. Okay, so essentially, how we think about this is it'll start moving when FA is just larger than FF, right? So the point that we want to know then is when FA is exactly equal to FF. When FA is exactly equal to FF, the net force is 0. If FA gets any larger, slipping starts, right? If FF is larger than FA, the block won't move. So you need to figure out the time when FA just gets larger than FF, okay? So essentially, what this problem then becomes is, let's find out when FA is exactly equal to FF, all right? So let's talk about what we defined. Well, we said that this is mg sine theta, right? Because it's based on weight, and weight is equal to mg. And that this is mu mg cos sine theta. All right, so let's put those in. I'm not going to do it all, but I'm going to set it up for you. Mg sine theta has to be equal to mu mg cosine theta. Okay, so m and g go away, right? They're in both sides. So then we get this. Sine theta equals mu cos theta. Okay, so how do we solve for theta at this point? Does that look familiar to you? What does sine over cos give you? Okay, or, you know, to solve this, theta has to be equal to the inverse tan of mu. Right? So that's the angle we're looking for, the inverse tan of mu. And that should work out to be about 11.3 degrees. And you can check it. You can try and see. Okay, you can put in those values and see if they work out to be equal numbers.